The orbital period and orbital radius for several of Saturn's moons are given in this table. And so you want to start by deriving the expression that relates the period with the radius. And we did this in the class notes. There's no need for me to go through the whole thing again. And the final answer that we got to was t squared is equal to 4 pi squared r cubed over gm. We could also write this, if you want to take the square root of both sides, as t is equal to, when you take the square root of everything, you get 2 pi r to the 3/2 power divided by the square root of gm. Keep in mind the m in right here in both of these equations is the mass of the object being orbited, which in this case would be Saturn. And it does not depend, neither of these equations depend on the mass of any of the moons. So, you want to do a graphical linearization on this problem to determine the mass of Saturn, the big M right here. So, I think the easiest way to do this is to plot, well, let's take the first equation and compare it with y equals mx plus b. And you can obviously see that there's no plus on here, so we can just say that the y-intercept would be equal to 0. On the y-axis, we want to plot t squared. So we can label that over here as t squared on that axis, and that's going to have units of, since t is in seconds, this would have units of seconds squared. And then on the x-axis, we want to have a function of the r. Remember, on both axes, we want to have functions of the two variables that are known. So we have the t squared on one axis, so I'm going to use one column in this table, one of the blank columns, to write a t squared. So we'll put t squared measured in seconds squared. And then for the other variable, we want to have a function of r. And in this equation, we have an r cubed in the numerator. So we'll say on the x-axis, I'm going to plot the r cubed. So I'll put that in the table up here, r cubed. That'll be measured in units of meters cubed. And I'll also put that on the graph down here. R cubed measured in meters cubed. Okay, so the next thing you'd have to do is take the 4 values of the period and square each of them. Now, because they're in scientific notation, you want to make sure you do this properly in your calculator. And what you should find is that the first value, you get an answer that is times 10 to the 9th. You get about 6.6 times 10 to the 9th. For the other 3 answers, you get something times 10 to the 10th. So just to make things easier, it actually helps if you write all the answers with the same scientific notation exponent, 10 to the 10th. So all 4 of these answers should have 10 to the 10th. The last 3, you already get an answer with 10 to the 10th. But the first one, where you got 6.6 times 10 to the 9th, you should actually rewrite that as 0.66 times 10 to the 10th. And then when you're plotting this on the axis, instead of just writing a t squared measured in units of seconds squared here, you can actually go through on this and write the units as, let me X this one off, and write the units as 10 to the 10 seconds squared. So then you only have to worry about the first part of the scientific notation right here. I think the last number in this list is like 5 point something. So let's just say it's basically going from 0 to 6. And you can see that that will work out because we have 0, 1, 2, 3, 4, 5, 6. The same thing happens with the r when you cube it. For the first value right here, you're going to get about 6.3 times 10 to the 24th power. But the remaining three values will all be times 10 to the 25th power. So for that first one, where you get 6.3 times 10 to the 24th, it's better to write it as 0.63 times 10 to the 25th power. And then just keep that same 10 to the 25th power for the remaining things with whatever the values are in the table. And then on the x-axis, instead of just writing r cubed measured in meters cubed, you can write r cubed measured in 10 to the 25th meters cubed. And this one should work out as well, because the highest value in this table, the last one was about 5 point something times 10 to the 25th power. So we're going from 0 to, let's just round this up to 6. And there are 12 vertical lines on here. So we can just say every other line, we can just go up by 1. So that'd be 1 times 10 to the 25th, and then 2, 3, 4, 5, oops, not right there, 5, and then 6 over here. So now it should be fairly easy to plot the points. You'll end up getting a graph that maybe looks something like this. I don't know exactly, but make sure it's a straight line that passes through all your points, and then you can put down for part D, because part B, all you're doing is just labeling already what you put on the two axes. Part C, we've drawn the graph, so part D, now we're just going to calculate the mass of Saturn. So if we go back to this equation and how it all matches up, we said on the x-axis was an r cubed, so basically everything left in front of that is going to be what's left, which is the slope. That little m is the slope. So if I circle all that stuff together and say that the slope, and again, I don't like using the lowercase m for slope because I think it's easy to get mixed up with a little mass or the mass of the satellite. So I'm going to change the slope to an s. So just say that the slope is equal to 4 pi squared over gm. And since it's the m I'm solving for, if I just rearrange that, I'll get the mass of Saturn is equal to 4 pi squared over gs. The value for g, I know, that's the 6.67 times 10 to the negative 11. And the slope, you're going to get it from just reading 2 points on the graph. Remember to try and read 2 points that are fairly far apart. So take a point down here and a point up here and use the slope formula, which is the y2 minus y1 over x2 minus x1. So I want you to solve the rest of this problem on your own, get a value for the slope based on the graph. Remember to include the scientific units on those things when you're plugging it into this formula, because that's going to make a pretty significant, it's going to make a pretty significantly large number ultimately for the mass of Saturn. So don't forget those. Calculate the mass of Saturn using this equation, and then just look up the mass of Saturn. And if you're pretty close, then you know you've done the problem right.